Okay, so let's get started. So we have covered this hidden Markov model, and today we are going to solve one question. And in the gate exam also, if they are going to ask you any question based on that Markov chain and hidden Markov model, so it will be similar to this question only. Okay, because this type of question can be framed from this particular topic. Okay, so first we are going to solve this question, and then we are going to proceed towards our next topic, that is probability inference. And we will see the basic introduction about probability inference and the algorithms that we have in this probability inference we will see in the upcoming lectures. So let me tell you, before starting, let me tell you also one thing, that in this uncertainty topic, in this AI subject, in this uncertainty topic, maximum 3 more lectures will be there and your syllabus will be covered. Okay, and then we will be starting that logic part. Okay, so after this one, maximum 3 lectures are required. Maximum and minimum 2, maximum 3. Fine. So not much is remaining now. Okay, so let's get started. And first, let's solve this one question based on hidden Markov model. So is this question visible to all of you clearly? I guess yes, it is visible, right? So let's first read the question, what it is saying. Consider the following hidden Markov model. O1 and O2 are supposed to be shaded. So what is O1 and O2 here? So carefully see this graphical carefully see this graphical representation or graph model here. So you can clearly find it out that O1 and O2, what are these? These are the observed states. Okay, O1 and O2 are the observed states. Right? What else? W1 and W2 here, they represent what? They represent the hidden states. They represent the hidden states. Fine. Now let's proceed. So here this CPT is given to you, conditional probability table is given to you, which we have also seen in case of Bayesian network. So you can also understand that Markov chain is just an extension of the Bayesian network also, because the similar type of concept we are using, right? And we have certain assumption, or you can say a strong assumption, a property, Markov property, which we call, right? That means the probability of the next state will only depend on the current state. That is the only assumption that we have. Okay, so these are the CPTs given to us. Now it says, suppose that we observe. Now carefully understand the question. Gurudeep, carefully focus here, and everyone also. Suppose that we observe O1 is equal to A and O2 is equal to B. Now carefully see, it is talking about a certain observed state variables. Yes or no? Like in our example, if you have watched the previous lecture, all of you, you will find that we were talking about, we have taken us a certain example, right? What will be the mood of the Tom, right, on a given day, whether it is sad or happy. So we talked about a certain state of observed variables, right? A certain, or you can say certain, basically the value of observed states, right, to be precise. So here also the values are given to us. O1 is equal to A, so we are observing this. O2 is equal to B. Now what else is given? So what else we have to find out now? So using the forward algorithm, now clearly it is mentioned, so certain observed states are given to you, right, and parameters are also given to you. Now you need to use the forward algorithm to compute what? To compute the probability distribution, probability of W2, this state W2, given these particular observed variables. Okay, one step at a time. Clear? So I hope the question is clear to all of you. So we need to compute this probability distribution, and it is not a difficult question, just the algorithm. If you recall the forward algorithm, if you remember, right, we use the dynamic programming, right? We divide that into 2 parts, and then further we divide it. So overlapping substructure were there, right? So the same thing we are going to use here. The same steps we are going to follow. So in the previous lecture, we have seen the algorithm. Now using that algorithm, we are going to solve this question. So this will give you the entire clarity of how it is happening and what we have to do in order to solve this question. Okay, so you will be able to relate with that algorithm now. Is this clear so far? Any doubt in the question? Shall we start solving this question now, everyone? Okay, fine. So now the first step. What is the first step? Step one. Step one is what? Initialization. So step one is initialization. Right? Step one is initialization. So you can initialize with t is equal to 1. Carefully see this. So when we talk about the initial probabilities, so if I ask you a simple thing, what is the probability of W1? What is the probability of W1? Now you will ask, sir, for what value you are asking? Whether W1 is equal to 0 or W1 is equal to 1. So we have two probabilities, right? Carefully see this. Carefully see this particular table. If I ask you the probability of W1, so here, can you see that initial probabilities are given to you? Already given to you. I told you in the previous lecture also, they will provide you in the question itself, right? Okay. So can I say, carefully say this. Can I say the probability of W1 equal to 0, that is given to us? So I'm writing all the information which we have also here in the table so that we can solve this question step by step and we should be able to understand it clearly. So probability of W1 is equal to 0. What is that? That is 0.3. That is 0.3. And probability of W1 is equal to 1. That is 0.7. So let's write it 0.3. Okay. Though you can directly use the table, but still just for, proper understanding, I'm writing everything here. Fine. So in step one, this is the first thing that we have to do. What is the second thing? Observed, or you can say observed probabilities or emission probabilities, if I talk about specifically. So we can say, what are the observed probabilities here? When O1 is equal to A, when O1 is equal to A. So again, carefully say this. Okay, so before proceeding, let me just ask you one simple thing. Are you able to understand this particular table? Carefully observe what it is given to you. Then we are going to proceed further. See, WT and WT plus 1. That means WT represents what? It represents the current state. Exactly. WT plus 1 represents what? It represents the next state. Correct. Now, what is given to you? It is given that probability of next state given current state. Okay. So here it is 0 to 0. So can I say, can I make this graphical model more representative? So let me do that for you. So here we have W1. Carefully see this. Here we have W2. We have O1 here. We have O2 here. That is the observed states. So can I say from this to this? From W1 to W1, because it is 0 to 0, that means from one state to same state. So can I say the probability of that is 0.4? Do you agree, everyone? Can I say this? Correct? Okay. From 0 to 1, it is 0.6. From 0 to 1, it is 0.6. So if from this state it goes to this state, then it is 0.6. Okay. Then what? Now, if it is 1 to 0, then it is 0.8. If it is 1 to 0, that means from this state back to the previous state, if I go, then it is 0.6. Right? So here the states are in terms of 1 and 2, but here we can consider them as, here 0, 0 represents the present state only. That means the W1. And from 1 to 0, that means from W2 to W1. Okay. And then 1 to 1 is 0.2. Is this clear so far? Even if you don't make this, then also you will be able to understand clearly. Just tell me, is this clear so far to everyone? Correct? Okay. Now let's proceed. Now let's observe this particular table. What it says. If it is 0 to A, that means probability of OT. Now OT can be O1 or O2, right? So here the values that they have substituted is for T, right? So OT given WT, that means from 0 to A, it is 0.9. From 0 to A, it is 0.9. That means from this to this, it is 0.9. This is what it is saying, emission probability. So I'm confused here as of how we are taking different possible values for states. different possible values. What kind of values? So here they are saying that, okay, let me make you understand. Here W1, W2 and O1, O2, they can have some values. This is the most generic, you can say, generic representation of graphical model they have given to you. Now they are not specifying in this graph, just I'm talking about in this graph, they are not satisfying what is the value of W1 and W2, right? In our example, let me relate it now. In our example, I took a specific value, right? That, okay, in the hidden states, we have what? We have rainy season and we have sunny, right? Exactly. And in the observed states, we have sad and happy. Yes. But here they are clearly mentioning using the CPTs here. So carefully see this. They have mentioned here. These are the values that they are using. So this is a generic form of representation that they have used in the graph, right? Here, just only in the graph, they are not mentioning everything. That is the reason why they have given you the conditional probability tables, all these tables. I hope now it is clear. Similarly, for observed state also, they have given you the values A and B, right? Accordingly, you have to solve. Make sense? Okay, good. So let's proceed now. So from W1 to O1, so as you can see, from 0 to 8 is 0.9. From 0 to B, that means, okay, that means from this to this, it is 0.1. It has to be 0.1 because the sum will be equal to 1 for, from hidden states to observed states, respective observed states. And again, from 1 to 8 is 0.5, from 1 to B it is 0.5. Is this clear? Do you have any doubt here? Anyone? Can you also make this with the given information? Is this clear? Do you have any doubt in this one? Just let me know once so that I can proceed further. Okay, so what we have done here, carefully see this, everyone. So what we have done here, from this current state to next state, when it is 0 to 0, that means we are at the same state only. So let's consider W1 as 0. So we are present at the same state. So it is kind of 0.4, right? When we are moving from 0 to 1, that means from one state to next state, then it is 0.6. So we can say the probability is 0.6. Okay. Then from 1 to 0, that means from here to here, it is again 0.6. Oh, sorry, it is 0.8. Okay, this is 0.8. I'm sorry. This is 0.8. Fine. And from 1 to 1, it is 0.2. Is this clear? Similarly, we have done it for the, from hidden states to observed state also, the same thing we have done. I hope now it is clear. 0.9, 0.1, 0.5, 0.5. Again, I'm saying you don't have to make this just by using the tables. In the exam, you don't have to make this, okay? This is just for your understanding purpose, nothing else. Just by using the tables, you can do it also. Okay, fine. So now if I talk about the observed probabilities, so these are what? These are the initial probabilities. These are the initial probabilities. You know what is initial probabilities, right, everyone? I was talking about in the previous lecture pi, right? I was talking about pi. What was that? That was the stationary distribution. That was the initial, that was the, yeah, you can say stationary distribution that we have to consider, right? Because we have to start from some node, right? So we need those initial probabilities here. So this is the same thing that we are talking about here. Okay, so this is given already in the question. Fine. Now what else? Now we need to talk about the observed probabilities, which we have already drawn, but let's write it here also. Now if W1 is equal to 0, if W1 is equal to 0, then what is the probability of O1 is equal to A given W1 is equal to 0? Can you tell me this? What is the probability of O1 is equal to A and W1 is equal to 0? By looking at the CPT, O1 is equal to A and W1 is equal to 0. Yes. Probability of O1 given W1 is equal to 0. Probability of O1 is equal to A. Yes, exactly. That is correct. That is 0.9, right? Probability of O1 is equal to A, given that W1 is equal to 0, that is nothing but the 0.9. Clear? That is nothing but 0.9. Fine. What else? If W1 is equal to 1, then what is the probability? What is the probability of O1 is equal to A given W1 is equal to 1? Can you tell me? Then it is 0.5, correct? Then it is 0.5. Yes or no? Correct. So then it is 0.5. Clear? So these are the observed probabilities when O1 is equal to A. When O1 is equal to A, these are the observed probabilities. Isn't W1 is equal to 0 and W2 is equal to 1? No, it's not like that. Maybe you are getting confused with this diagram representation. See, understand this thing. W1 can have two values, 0 or 1. W2 also can have two values, 0 or 1. Is this point clear to all of you? Okay. Like here, if you see, carefully see this one. W1 can have 0 value or 1 value. So probability of W1 is 0.3, probability of W1 is equal to 1 is 0.7. So why these initial probabilities are given to you? Because you need to start from somewhere, right? You have to start from this one. So if you remember, we have written the joint probability distribution expression, right? In the previous examples. So we wanted that probability of weather being sunny, right? Just to start with. So these are given to us. So W1 can also have the value 0 or 1. W2 can also have the value 0 or 1. Is this clear? Any doubt, anyone? Okay, fine. So now we have the initial probabilities. Now we have the observed probabilities. So what should be the next step? If you remember that tree, when I was explaining you the dynamic programming, how DP is used for this particular model. So what should be the next step? Anyone? What should be the next step? What should I calculate now first? Think about it. I'm giving you some time. Alpha 2. Yeah, we have to, eventually you have to calculate alpha 2. That is absolutely correct, Manjunath. That is absolutely correct. But in order to calculate alpha 2, what do you need? Come on. In order to calculate alpha 2, what do you need? Can I say you need alpha 1? Yes or no? That means you need the base conditions. Carefully see this. What we did, we basically divided the problem. Into, there we had 3 steps. Now we have 2 steps only. So alpha 2, and here also it is going to be alpha 2. Now it's up to us what value we are considering. Let's say alpha 2 of W1, alpha 2 of W1. Now here alpha 2 of W1, you can write like this. Because as we know in this example, we know that W1 can take either 0 or 1. So it can be 0 here. Similarly, here also you can write. Now this time, maybe W1 is taking the value. Okay, it should be, it should be W2, not, my bad. Just a minute. It should be W2. I'm sorry. W2, here it is 1. Is this clear? Why I'm writing like this? Carefully see this. This is what it is given to you. Correct? This is what it is given to you, everyone. Okay. So at step 2, we are talking about W2, right? If you remember, if you related, now try to relate it with the algorithm that we have studied in the previous class. We are starting with this step 2, right? Now we are assuming either W2 is equal to 0 or W2 is equal to 1. Either it is rainy or it is sunny. Yes or no? Either this state is rainy or it is sunny. Correct? So either W2 is equal to 0 or W2 is equal to 1. So can I say I have to start with alpha 2 where W2 can be 0, alpha 2 where W2 can be 1. And then further you are going to divide this one, also this one. So if I divide this one, can I say here it should be now alpha 1, W1, because at the first step you have what? W1. Now W1 can be 0 or W1 can be 1. Similarly here also W1 can be 0 or W1 can be 1. Is this point clear now? Are you able to relate it now? Take your time, carefully see this, and then let me know. All good? Okay. Nice. So in order to calculate this and this, can I say you need these base conditions first? You need to calculate these base conditions first? Yes, obviously. So now let's calculate the base conditions. I can just erase this one because I've already made there. Right. So now we can compute the third step. Now we can compute what? Compute alpha 1 of W1. Correct. Now, as I told you, there are two possibilities. Alpha 1 W1 is equal to 0 or alpha 1 W1 is equal to 1. Either this can take the value 0 or it can take the value 1. So you need to compute both. So alpha 1 W1 is equal to 0. This is what we can calculate. Either you can write this way. See, either you can directly write this also. That is also valid. Because this is same as what? It is same as saying that W1 is having the value 0. So probability of what? This is equal to what? Probability of, can anybody tell me what it is equal to? The base conditions. Do you remember how we calculate this? It should be probability of W1 being 0 multiplied by probability of O1 given W1. Yes or no? Correct? Correct? Because when we are talking about step 1, this is what we have, right? Okay. So we can say probability of W1 is equal to 0 multiplied by probability of O1 is equal to A, because it is given in the question that we have to consider this value, given W1 is equal to 0. Fine. Now what is the value of this? Probability of W1 is equal to 0. That is 0.3, right? Yeah, that is 0.3. That is 0.3. So we can write here 0.3. Okay, and what is this value? O1 is equal to A, W1 is equal to 0. That is 0.9. So you will be getting 0.27. Similarly, we need to calculate this also. So where W1 is equal to 1 now. So I can write the same thing. Probability of W1 is equal to 1 multiplied by probability of O1 is equal to A given W1 is equal to 1. So this is 0.7 multiplied by 0.5, right? 0.5, yes, 0.5. So what do we get? 0.35. Is this clear so far? Any doubt here? If you have any doubt, please ask. These are the base conditions. These are the base conditions that we have computed. Because we cannot further split alpha 1, right? We cannot split because there are only two steps, the second step and the first step. In the previous example that we have considered in the previous lecture, there were 3 steps, alpha 3, alpha 2, and then alpha 1. Here we have only 2 steps. Fine. Now what? So we have computed this, and obviously once you have computed this, you can use the value here. That is the benefit of DP, right? Once you have computed this, you can use the value here. Fine. Now let's focus on this value. How can you compute this value now? So come to this, focus on this one now. So if you remember clearly, so alpha 2, now we have to compute what? Alpha 2. Alpha 2 of 0, can I say alpha 2 of 0? When I say alpha 2 of 0, that means what? That means probability of, that means you can say the value W2 is equal to 0, right? That means the value W2 is equal to 0. So in short, we can write alpha 2 of 0. Okay. Now how we can write? We know that we need this value multiply by what? Multiply by probability of W2 given W1, yes, plus this value multiply by probability of what? W2 given W1. Okay, let me just write it first, then you will be able to understand clearly. Okay, carefully see this, everyone. Alpha 1 of 0, because we are talking about 0. So alpha 1 of 0 multiplied by probability of W2 equal to 0 given W1 equal to 0, right? You can write multiply by, let's do it here only. We can take common, or but you can do it here. Given multiply by probability of O2 given W2, and O2 is equal to B, right? As per the question, we have to consider O2 is equal to B given W2 equal to 0. Is this clear so far? Plus, if you have your notes handy with yourself, or like just now, whatever previous lecture we have discussed, just open your notes and just read the formula. Okay, you will be able to relate it. So this is what? This is now alpha 1 of 1 multiply probability of what? The same thing, but now the value will be what? W2 is equal to 1 given W1 is equal to, okay, W2 is equal to, sorry, 0 given W1 is equal to 1. Yes or no? Can I say this? Okay, it should be 1 only, right? It should be 1 only. Yes. Is it clear so far? Any doubt? Multiply probability of O2 is equal to B given W2 is equal to 1. This is how you can calculate alpha 2 of 0. Take your time. And if you have any doubt, please ask. This should be 0, right? This should be 0. Okay, let me explain you again using the diagram. Carefully see this, everyone. Let me make this diagram here. That would be better instead of going again and again to the backslide. W1, carefully see this, everyone. W2, O1, O2. Now, when I'm talking about calculating alpha 2 of 0, so this 0 represents that I'm talking about W2 being 0. This is clear to all of you, right? Alpha 2 means I'm talking about, I'm present. You can say you are present, you are standing over here at the second step. Fine. So you are calculating this. And we also know this, that this is alpha 2 of 0, alpha 2 of 1. And we have divided this alpha 1 of 0, alpha 1 of 1. So as of now, I'm talking about this part. Correct? This is also clear. Okay. So is equal to what? Alpha 1 of 0 multiplied by what? Now, don't consider this. You can just ignore this part also, because that is not required, because we are talking about, we are standing here at the second step. Now, this is relevant. You have something here, but we don't care about it. Okay. So alpha 1 of 0, that means W2 given, can I say probability of W2 given W1? This is clear. This thing you know already, right? Now just substitute the value. W2 is equal to 0, because that is what we are considering. And W1 also being 0, because alpha 1, 0 we are considering. Here alpha 1 of 0 means what? W1 is equal to 0. Here alpha 1 of 1 means what? W1 is equal to 1. Correct? Okay. So multiply by, then this also you have to consider O2 is equal to B multiply, probability of O2 is equal to B given probability of, given W2 is equal to 0. So this is how we are writing. right? Plus alpha 1 of 1 plus alpha 1 of 1. Now alpha 1 of 1, the same thing. Formula is exactly same, just the values are different now. So alpha 1 of 1 into probability of W2 given W1. W2 is 0, W1 is 1, because alpha 1 is 1, right? Now multiply probability of O2 given W2. Probability of O2 given W2. What you have done here, the same thing you are doing here, just the value of W2 here. Now you are considering 1, because this is what? This is okay, sorry, this is also 0, right? Yeah, this is also 0. Just a minute, because W2 is equal to 0, right? Yeah. Clear? So O2 is equal to B given W2 is equal to 0. So for this entire part, W2 is 0. So I'm talking about this part. For this entire part, you can see clearly W2 is 0. For this part, W2 will be 1. So we will be solving that also separately. Is this clear? Again, carefully see this. If you have any doubt, please ask again. I will explain again also. Everyone. Abhas, Gurdeep, Manjunath, Chandana. Are you able to relate it now with the algorithm? The same thing we are following, right? Nothing different. In the algorithm also I explained you same things, but now here we are solving a question. That is the difference. Shall we proceed now? So let's substitute the values also. Okay. So let me write the values here with red color so that we don't have to write it again, this formula. So what is alpha 1 of 0? We have calculated already. Alpha 1 of 0 is 0.27. Okay. So it is 0.27 multiplied by probability of W2 is equal to 0 given W1 is equal to 0. And what is that? Now this table will be handy for us. Probability of W2 is 0 given that W1 is 0. Can I set as 0.4? Can I set as 0.4, everyone? Yes, it is 0.4. It is 0.4. What about probability of O2 is equal to B given W2 is 0? O2 is equal to B given W2 is 0. Can I set as 0.1? Exactly, very good. It is 0.1. It is 0.1. Okay. So probability of O2 is equal to B and W2 is equal to 0. So that is 0.1. Fine. So that is 0.1. Okay. What about alpha 1 of 1 that we have calculated just now? That is 0.35. Multiply by probability of W2 is equal to 0 given W1 is equal to 1. W2 is equal to 0. Come back to here. W2 is equal to 0 given W1 is equal to 1. Can I set as 0.8? Correct. So it is 0.8. Multiply by O2 is equal to B given W2 is equal to 0. That is same, right? That is same only, 0.1. Is this clear? Do you have any doubt? So can I say these two things? I mean, these things are common. So you can also write it separately, or you can write it here like this also. Nothing will be changed. You can take it common, or you can write it, in both the parts, left part and right part also. Now, if you compute this, what do you get? So let me add one slide here. Now, if you compute this, so alpha 2 of 0. So 0.27 into 0.4 into 0.1. Can you do it? Let me do it also. 0.27. 0.27 multiply by 0.4 into 0.1. Okay. Then yes, that is correct. Plus it is 0.35 multiply 0.8 multiply 0.1. It is 0.0388. Exactly, that is correct. So it is, yeah, that is absolutely correct. 0.0108 plus 0.028, and that is equal to 0.0388. Similarly, we can find alpha 2 of 1 as well. Now I want you to write this equation, just try to write this equation in your notebook, not here in the chat, just in your notebook by seeing this diagram. Okay, try to write it for alpha 2 of 1, just for your practice purpose. And once it is done, just let me know in the chat. Then I will be writing it. Alpha 2 of 1. Is it done? Okay, let's write it now. So alpha 2 of 1, what will be the value of alpha 2 of 1? So you need alpha 1 of 0, right? And you can just write plus here. And what else you need? You need alpha 1 of 1 also. Now you can write the equation completely. So multiply by what? The probability of W2 is equal to 1 given W1 is equal to 0, because here it is 0. Multiply by probability of O2 is equal to B given W2 is equal to 1. I hope you have written the same thing. Probability of W2 is equal to 1 given W1 is equal to 1. Multiply by probability of O2 is equal to B given W2 is equal to 1. Correct? Okay. So now we can substitute the value W alpha 1 of 0, that is nothing but 0.27 only. So these values are as it is 0.27, and this is what? 0.35. 0.35. And what about this one now? Probability of W2 is equal to 1 given W1 is equal to 0. W2 is equal to 1 provided W1 is equal to 0, that is 0.6, and 1 is 0.2. Okay. So here it is 0.6 and this is 0.2. And what about this value? O2 is probability of O2 is equal to B given W2 is equal to 1. O2 is equal to B given W2 is equal to 1. That is 0.5. That is 0.5. 0.5, and here also this is same 0.5. Okay, now let's solve this quickly and let me know. After solving this question, I will let you know what type of like what questions they can ask from this single question. Actually, this single question is having multiple questions in it. But before that, just try to solve this. Okay, that's nice. Let me write it here. Alpha 2 of 1. Alpha 2 of 1, that is nothing but 0.081 plus 0.035, and that is equal to 0.116. Now, let me ask you one thing. Let's say if you can answer this or not. Ideally, when I'm talking about the joint probability distribution, right? When we are talking about joint probability distribution, when O1 is equal to A, O2 is equal to B, right? So when I'm splitting this up, right? When I'm splitting this up, also it is, W2 should also be there, right? W2. And W2 can be 0 or 1. So based on that, what we did this thing. Correct? And then we further divided it. This is what we have done actually. Okay, let me just write this also for you. Now, this value that is coming up is 0.0388, and this value coming up is 0.116. So to find this, can I say I need to add these two values and then I will be getting the final answer? Do you agree? Yes or no? But if you are finding the probability, the sum should be equal to 1. If you add these two values, is it equal to 1? No, they are not equal to 1, right? Then what is the problem? We have to normalize this. We have to normalize this. So if you remember, in the previous lecture also I told you that when you are writing this, carefully see this, probability of x given y, Bayes theorem, using Bayes theorem, what we write? Probability of y given x into probability of x divided by probability of y. Yes or no? I told you that this is total probability, right? So we basically remove this, but in order to remove this, you have to normalize it. So how can you normalize this? So basically, if you divide it by this, because this is going to be same, right? I told you this is going to be same for every value of x. So if you divide, so whatever values that we are getting here, this value and this value, if you divide it, so now for the final step, that is normalize. Normalize to find what? Probability of W2 given O1 is equal to A and O2 is equal to B, because this is what we have to find, right? Finally, correct? Is this clear? So what we have evaluated so far, if you carefully observe, this is nothing but, can I say x intersection y? Do you agree? This is this value, just the numerator part, that is x intersection y. Can I say this is what you have calculated? This is what you have calculated. So if you divide these two values by this total one, so can I say then you will be finding this posterior probability, which is what we have to find in the question. This is what we are trying to find out. So it's very simple now. So carefully see this. Now probability of W2 is equal to 0 given O1 is equal to A, O2 is equal to B. How can you find it out? Now for specific value we are finding out, right? So it is going to be what? Alpha 2 of 0 divided by alpha 2 of 0 plus alpha 2 of 1. This is how we normalize it. In ML also you might have seen this, how we can normalize this, right? So this is how we can just add two values and divide it by that. So it is going to be what? 0.0388, right? Divided by 0.0388 plus what was the value? 0.116. Okay. So this value will come out as 0.25. Similarly, you can calculate W2 of 1 given O1 is equal to A, O2 is equal to B, right? So now you can write here, that is nothing but alpha 2 of 1 divided by alpha 2 of 0 plus alpha 2 of 1. So this value will be 0.116 divided by 0.0388 plus 0.116, and that will come out as 0. Obviously 1 minus 0.25, so this will come out as 0.75, and that is your answer. Is this clear? Do you have any doubt? This is the complete solution of this question. And this is not just one question. There are multiple questions that can be asked from this one only. Like, for example, they may ask you what? They may ask this question also. Let's say probability of, what is the probability of W2 given, W2 is equal to 0 given W1 is equal to 1. So simple questions also they can ask, right? And this is the maximum, you can say, the like beyond this, they are never going to ask you in the gate exam. From this HMM model, this is the last thing that they are going to ask from this question. Now they may ask you a simple question also, right, from this one. Is this clear so far? Do you have any doubt? Okay, fine. So instead of asking, you know, both the values, they may just ask you this value also. For example, in this question here, carefully observe this. They have not mentioned the value of W2, whether it is 0 or 1. That's why we are finding it for both. So it may also happen that they will provide you this value. Let's say probability of W2 is equal to 0, given O1 is equal to A and O2 is equal to B. Now you just have to find this value, and this is nothing but alpha 2 of 0, right? And you normalize it also, and that will be your answer. So subparts can also be asked. I hope it is clear. Beyond this, they are never going to ask you anything in the gate exam. That is for sure. 99% I'm saying that is for sure, because these type of questions can be framed based on this. Okay, fine. So we have solved the question as well. Now we can proceed to our next topic, that is probability inference. So far what we have seen, you know, the Bayesian network, we have seen the Markov chain, we have seen the hidden Markov model. So let's understand what is this probability inference. So a probabilistic graphical model, M represents a unique probability distribution P over a set of random variables. So whatever graphical models, like HMM also, right, Bayesian network, all these are graphical models, probabilistic graphical models that we have seen so far. Given such a representation, the following are some of the important tasks that we can accomplish. What tasks we can accomplish? Querying or an estimation. So querying means what? Computing the likelihood of certain variables, right, that we have seen, optionally conditioned on other set of variables. So we can query certain you know, likelihood, like what is the like we have seen also in the previous lecture, the one part of hidden Markov model, that is likelihood. So what we did in likelihood is nothing but Viterbi algorithm. We basically use Viterbi algorithm for likelihood, right? So basically we are trying to inference the probability of certain variables given another set of variables. So this is generally called as probabilistic inference. So we have used those models, that is hidden Markov model, for that. Okay. An estimation, when the model itself is unknown, estimating a plausible model M from data D, this process is called learning. So we also talked about learning. In the previous lecture. So they are part of this probabilistic, probabilistic models that we have studied. So we discussed likelihood, we discussed decoding, and we discussed learning. So learning phase comes when we talk about, determining the or estimating the probabilities, transition probabilities, that is emission probabilities, and the probabilities from one hidden state to another state. So we talked about that, right? We can estimate it and we can train our model. So basically we use EM, that is estimation maximization, and basically this Baum-Welch algorithm. That is not important for your exam point of view, but you should just know it, that exists. So there we try to learn, we try to estimate the probabilities of the model. So now, but our current focus is on inference. So though learning is usually seen as a task different from inference, it is not always the case. Learning typically involves estimating parameters, right, of the model M so that it explains or fits the data D, right? In Bayesian learning, we particularly seek probability of M given D, that is probability of model expectation maximization. Yes, I said something different. EM model, right? Oh, I told estimation, right? Expectation maximization, yes. Okay, my bad. Okay, my mistake. So we particularly seek probability of M given D, probability of model given data, which is done by assigning prior distribution PM over the parameters and then estimating the parameters over the given data. So this is the same thing that we have seen so far, and which is essentially the inference. So basically we try to infer from these models. Sometimes learning has to be done from incomplete data. And in such cases, when the data is not complete, in such cases, we run inference to estimate the hidden variables representing the missing data. So sometimes when the data is not completed, then we have to infer from whatever information we have, right? So there are three important kinds of queries given a distribution represented by the graphical model, that is likelihood, posterior belief, and most probable assignment. So let's see one by one what they are talking about. We know already these things, but let's see this. Likelihood is what? This is the value of the marginal probability of a subset of variables in the distribution. So as you can see here, likelihood is also calculated to get the conditional probability of different set of variables conditioned on E, right? E is called nothing but the evidence. That means you can say the denominator that we have, that is nothing but the evidence, right? So when we write the Bayes theorem, that is nothing but the evidence. So here also they have calculated this only, right? So let us define a joint probability distribution P over variables from 1 to n. See, these whatever slides I'm showing you, these are not important. Just to get an idea of what we are trying to follow now, you will understand. Okay, in some time you that all makes sense. So E is what? E is all the random variables from xk1 up to xn. And to calculate probability of E, we do this following. That means we calculate the joint probability distribution and we sum over it from x1 to xk. What is posterior belief? Posterior belief is nothing but the conditional probability only, right, of some query nodes conditioned on an evidence. So probability of x given E, you know all these things. That is nothing but probability of x comma E divided by probability of E. Probability of E, this is the total probability, and this is the joint probability distribution. Clear? And there is a subset that we do not care about. Yeah, that is fine. We can proceed further. Okay. So you can just give it a read later on. I don't want to read it for you. You can do it. Okay. And then most probable assignment. So like we have MLE. So similarly, we have MPA also. Most probable assignment. So if you remember, we calculated this, right? In which algorithm? Which algorithm we were doing this? In Viterbi algorithm. If you remember in the previous lecture, we have covered that. So we were trying to find out the maximum probability for Y given E, right? So in Viterbi algorithm, what we were doing? We were trying to find out for which, like given the observed states and the parameters, for which hidden states the probability will be higher, right? And we were trying to find out the maximum of, we were trying to find out all the probabilities and then find out the maximum of all. So that is nothing but most probable assignment. Most probable assignment. Okay. MP has their direct applications in tasks like classification and explanation. That is fine. We can proceed further. So now when we have, like, so far, if you see, we have considered the graphical models which are simpler, not very like where we have 2 nodes, 3 nodes, 4 nodes, 5 nodes, 6 nodes. But if we have a lot of nodes, then what we do? Then that will be very complex to compute, right? That will be very complex to compute. There we talk about the inference. There we talk about the inference, and we have certain algorithms for that also. So complexity of inference, as it is mentioned, computing probability of x is equal to x given E is in a graphical model is a NP hard problem, which means there is not generalized efficient algorithm. There is no generalized efficient algorithm for inference given a probabilistic graphical model or query or evidence nodes. As I told you, if we have a lot of nodes, then there is not any generalized efficient algorithm for that. Okay, and this is NP hard problem. So however, for some families of models, there are polynomial time algorithms for inference. So we basically divide the inference into 2 parts, probability inference into 2 parts. One is exact inference and other one is approximate inference. So exact inference is when you can find out the exact probabilities distribution using certain algorithms, when it is possible to compute exact exact probability distribution, when it is possible to compute. But if it is not feasible to compute, then we use approximate inference. Okay, then we use approximate inference. So I'm just giving you the overview. We are not understanding the algorithm as of now, that we will see in the next lecture. For exact inference, we have one algorithm called as variable elimination algorithm. The second one we have is message passing algorithm. The third one we have is junction tree algorithm. If you see the syllabus of gate DA, you will find that only this part is present in your syllabus. So they have clearly mentioned that exact inference using variable elimination. If you have seen the syllabus carefully, you will find that variable elimination algorithm only you have to study. But there are other algorithms also, and also we are not going to talk about them, because if it is not in the syllabus, then it will be as of now, for exam perspective, that will be wastage of time, I would say. So this thing we are going to cover, variable elimination algorithm. In the next class, we will be starting up this one. So we have other algorithms also, but we are not going to talk about it. And for approximate inference, we have stochastic simulation, we have Monte Carlo methods, we have variation algorithms. So basically in the GATE TA syllabus, it is mentioned that when we talk about approximate inference, we have to consider only one method, that is sampling. So there are two types of sampling that we will be talking about. One is your Gibbs sampling, and second one is your Monte Carlo sampling. These two are there in your syllabus. So this part and this part is the only thing that is remaining in uncertainty topic. The rest everything is covered. Clear? So you can just give it a read to these things. Exact inference. So as you can see here, exact inference refers to the process of computing the exact probability distribution or the exact values of interest from a probabilistic model. Right? There are certain examples of exact reference. So using Bayesian network, but the algorithm that you are going to use is variable elimination or the junction tree algorithm, or I told you the third one, that is nothing but message passing also. So using Bayesian network, we will be using these algorithms. We will be applying these algorithms on Bayesian network. We will be applying variable elimination algorithm on Markov chain as well. We can apply these algorithms on hidden Markov model as well, right? But we will see mainly the Markov chain, how we can apply variable elimination on Markov chain, because Bayesian network is just, Markov chain is just the extension of Bayesian network, nothing else. And hidden Markov model, that is not required for your exam point of view. Okay. So similarly for Markov chain also, for HMM also, we can apply these set of algorithms for exact reference. And then we have approximate reference. As I told you, it is used when exact reference is computationally infeasible, right? It involves finding an approximate solution that is close enough to the exact result, right? And obviously when you are finding the approximate, when you are doing the approximate inference, there will be some drop in the efficiency. So as it is mentioned, approximate inference methods trade off some amount of precision for computational efficiency. And as I told you, there are certain examples of approximate inference, that is sampling methods. So this is there in your syllabus. Techniques like Markov chain, Monte Carlo, MCMC methods includes the Metropolis Hastings algorithm and Gibbs sampling. So this is there in your syllabus that we will talking about. And it generates basically the samples from posterior distribution to approximate it. I know most of the things are not making sense as of now to you, but you will understand. Like you have understood till the HMM clearly, you will understand these methods also clearly. Okay, so don't think about that. Don't think much about it. I know how to cover these things in a lot of detail and with clear understanding. Okay. Again, there are other methods also for approximate inference, that is variational inference, loopy belief propagation, expectation propagation. But again, these are not in your syllabus, not in syllabus. So you can be relaxed. I have just mentioned this on the slide so that you should be aware of it, that okay, these things are also there. Okay, that is the only reason why I've added this. Otherwise I could skip it also. I could directly mention that sampling methods that we were talking about and this variable elimination. So is this clear so far? Do you have any doubt? That's it for today's class. This overview, little bit, I hope, making sense to you. But actually what we are doing in these algorithms, you will understand once we proceed with these algorithms in the next lectures, upcoming lectures. But before this, just probability inference, if you just skip this part, before this, whatever we have covered in this uncertainty, is that crystal clear to all of you? Do you have any doubt? So you will be able to handle every question, right? Whatever they ask from this topic, because we have covered the questions as well. And 99% of time, they are going to frame the question similar to this only, nothing else. Because if you have seen GATE DA 2024 exam also, they have not asked question based on HMM in GATE 2024. But this time it may be possible that they ask question from HMM or Markov chain, or you can say. This is quite possible this time. But we have covered Bayesian network and both as HMM, so we will be able to solve any question if they ask from these topics. And definitely there will be question either from Bayesian network or from HMM for sure. Okay. So that's it for this class, and I will see you in the next class, and we will be starting variable elimination algorithm. Okay, for exact inference. Okay, that's it from my side. We'll see you in the next one. Thank you, everyone. Good night. Take care, and bye bye. Thank you all.